Today we looked at 3 different puzzles regarding related rates. And tonight what I'm going to do is I'm going to do 3 examples of the typical type of problems you will see with related rates. Pythagorean theorem, volume and area, and then angles with some trigonometry. So let's look at our first example. Okay, our first example involves Tweety Bird. Tweety is resting in a birdhouse 24 feet off of the ground. So here's his little house, quite high. Using a 26-foot ladder, which he leaned against the pole holding the birdhouse, Sylvester is trying to get Tweety Bird. Well, Sylvester tries to steal the small yellow bird. Tweety's bodyguard, Hector the dog, starts pulling the base of the ladder away from the pole at a rate of 2 feet per second. How fast is the ladder falling when it is 10 feet off the ground? Interesting problem. Well, what we're going to do is we're going to use a graphic organizer to solve these problems. Now, you will not have to use this graphic organizer every time, but in the beginning it kind of helps you know what parts are needed for a related rates problem. And the first thing you need to know is what is the given rate of change? Well, we are told that the change of the ladder moving away from the pole, so dx dt, is 2 feet per second. Now, what is your unknown rate of change? Well, we're wanting to know how quickly that ladder's falling. So that's going to be dy dt, and that is our unknown. And we want to know what is that rate of change when y equals 10. So these are a couple of the facts given. Now notice I've drawn a diagram. You'll need to draw a diagram for nearly all of these. And you label the diagram with the important parts. Now as you can see, x is changing, the length of the ladder, the ladder from the wall, and then y is changing, the height of the ladder from the wall. So what is constant in this problem? Well, the only thing constant is z, which is the length of the ladder. And what is varying? It's the height of the ladder in respect to the Tweety Bird's house. And we know that it starts out at 24 feet. So what we want to do is write an equation using related rates. When you look at your diagram, you notice that you're going to be using Pythagorean theorem. So it's going to be x squared plus y squared equals z squared. Now before I look at the rates, I'm going to substitute any values that are constant. And since the ladder is constant, we're going to substitute 26 in for z. Now I'm going to take the derivative in respect to time and look at all of these rates. So we get 2x and then a little implicit differentiation going on. So it's dx dt, and then it's plus 2y dy dt. And of course the derivative of 26 squared is 0. Okay, now we have 2 unknowns. We're wanting to solve for dy dt. How can we use this information? Well, we do know that we want to find out, in looking at this triangle, it's 26, and we want to know the change in y when y is 10. Well, can we find this value of x? Sure we can. Pythagorean theorem. 10 squared plus what squared equals 26 squared. Well, I did the math, and I'll just let you know that it is 24. So we end up with 2 times 24, and then the dx dt is 2 plus 2, and then the height of the ladder we want to know is 10, and we do not know dy dt. That's what we're solving for, is equal to 0. So we do the math, and we get 96 plus 20 dy dt, and solving for dy dt, we end up with dy dt is equal to negative 24 over 5, and then always have to use units, feet per second. So then to answer the question, when the ladder is 10 feet off the ground, it takes some time to write. The rate of change of the ladder is negative 24/5 feet per second. Now it's negative because the ladder is falling down. Okay, now let's look at another typical problem. Our second typical problem generally will deal with volume or surface area. And we did a problem like this in class, where we have a water tank and it's an inverted circle cone with a base radius of 2 meters and a height of 4, kind of like in class where the height was twice as large as the radius. Now we do have a constant rate, 2 meters cubed per minute is being pumped into the tank, and we have to find the rate at which the water level is rising when the water is 3 meters. Okay, and they give us the formula for volume. So let's go ahead and set this problem up. So we first have to see what is the given information. Well, we were told the change in volume in respect to time is equal to 2 meters cubed per minute. Now what we're trying to find out is the change in height in respect to time. So that's what we don't know. And we want to know specifically when h is equal to 3. Okay, so what is constant about this problem? Well, the ratio was constant between radius and height, but we might not actually use those numbers because we don't know that the water will get that high. So, we could say r is 2, height is 4, but this is just mainly a proportion relationship. Okay, now what's varying? The height, because we're going to want to know when it's 3 meters. So now looking at this, they told us what equation we're going to use. It's 1/3 pi r squared h. Now you can see here, I've got two variables, right? Like I don't have anything really to substitute into this function, so I only have one variable. But I do know this relationship of 2 to 4. And so we know that when we're looking at the relationship between radius to height, it is a 2 to 4 relationship. And so then we would know that radius, actually, if we cross multiply, we get radius is 2h over 4, which is h over 2. So what we can do is we can rewrite this so it's all in terms of h. Now I'm leaving it in terms of h because I want to know when h is 3. So I have 1/3 pi, but instead of r squared now, it's going to be h over 2 squared times h. Okay, does that work for you? So now we're going to take the derivative of this function. Now before I do that, I should maybe clean it up a little bit. And so I get 1/3 pi, and this is h squared over 4 times h, right? So actually I get 1 over 12 pi h to the third. That will make it quite a bit easier to take the derivative. So when I take the derivative then, we have bring the 3 in front, so we get 3/12 pi h squared, and then it's the derivative change in height in respect to time. So now we substitute in those values we want to know. Well, we know the change in volume over time is 2, and then 3/12 is 1/4 pi, and we want to know when the height is 3 squared, dh dt. So now I just isolate the dh dt. And by doing that, so we get 9 pi fourths here. So 2 equals 9/4 pi dh dt. And so I'll multiply by the reciprocal. So I end up with 8 over 9 pi dh dt. Okay, now the units for this would be, is it miles per minute? Probably meters per minute. So the change in height is 8 over 9 pi meters per minute when the height is 3. Great, let's do the last problem now. Now the last problem is going to do with angles in trigonometry. So you've got a hot air balloon rising, again it looks like an atomic bomb, and you've got someone sitting right here who's tracking it, so you can see their field of vision. And we're told the angle is pi fourths, and we're told a rate of radians per minute. So let's use this information to fill in our graphic organizer. Okay, so what is the given? We are given the change in the angle. So change in theta over change in time is equal to 0.14 radians per minute. Now what we don't know is the change in y over change in time. Let's see, constants. The constants is the guy sitting and watching this hot air balloon, so that's 500 feet. Varying is we've got the rate of change of the theta, and then also the angle of how he's looking at the hot air balloon is pi fourth. So looking at this diagram then, I want to use a trig function that does use 500 because that's a constant, and also I'm going to want to use y because I'm looking for dy dt. So it's opposite and adjacent, so that leads me to tangent. So we know that tangent of theta is y over x. And x is a constant, so we have tangent of theta is equal to 1 over 500 times y. Now I just wrote it like that so it's easier sometimes to take the derivative and such. Or you could even make it, well, you could even go 500 tangent theta is equal to y. So now we're going to take the derivative of y in respect to time. So we get dy dt, and it's going to be 500, and we know the derivative of tangent is secant squared theta. Now what values can we substitute that were given to us? Well, we were told, oh, you know what I forgot? I forgot change in theta over change in time. That's probably one of the most common mistakes, just like I made, is remembering to use implicit differentiation. So we want to solve for dy dt. So we have 500 secant squared. Now we know that theta is going to be pi fourth, and the change in theta over change in time is 0.14. So in doing the math, it's nice because secant of pi fourth, I believe, is radical 2, and then squared would be 2 times 0.14. So I get out the calculator there, and it turns out to be 140, and we must always include the units. So let's see, I know it's minutes and it's feet, so it's feet per minute. So when the angle is pi fourth, then the height of the balloon, the rate of the height of the balloon will be changing at 140 feet per minute. Now I'm going to have you try one. So here is your problem, and you have to find the rate of change of area. So pause the video and answer the question. Now here's the solution. Now notice right here I identified what I was given and what I wanted to find out. Here's the function. I took a derivative of it and plugged in everything I knew. The one thing I initially forgot was that it's area, so the units are centimeters squared per second. Now using the same values, would you find the rate of change of perimeter? So pause the video and answer the question. So here's my work. Again, this is the given information. Here's my perimeter formula. I take the derivative and I end up with 0 centimeters per second. Using the same facts, will you now find the length of a diagonal of the rectangle, its rate of change? Pause the video and answer the question. So again, here are my facts. And because it's a diagonal, then we're going to use the Pythagorean theorem. So I'm going to find the derivative of that, which does require a little bit of chain rule. And I get negative 14 over 13 centimeters per second. Last of all, which of these quantities are decreasing and which are increasing? The area is increasing because its derivative is positive. The perimeter is not changing because it has a value of 0. And the diagonal length is decreasing.